Early in the morning of June 30, 1908, in the remote Siberian taiga, nomadic Evenki herders were asleep in traditional skin-covered tents, known as chums. Without warning, the sky fractured. Eyewitnesses reported a flash of light as bright as a second sun, followed by extreme heat and a deafening roar. An aggressive shockwave knocked the herders off their feet, rendering many unconscious. This map illustrates the sheer scale of the destruction. The blast released 10 to 15 megatons of energy, roughly 1,000 times the yield of the atomic bomb dropped on Hiroshima. The expanding radius flattened 80 million trees across an 830 square mile area, a footprint easily capable of engulfing modern-day London. The total output of energy over this isolated forest makes it the most powerful impact event in recorded history. Because the Earth is constantly rotating, timing determined the target. If the exact same cosmic object had arrived just 5 hours later, the impact zone would have shifted westward, detonating directly over St. Petersburg and obliterating the Russian capital. The event was documented largely because of agrarian reforms initiated by the Russian Empire. The expanding Trans-Siberian Railway brought a sudden influx of peasants into the Siberian wilderness, providing a network of witnesses to the disaster. In the days that followed, bizarre atmospheric anomalies stretched across the globe. Vast quantities of dust and ice crystals in the upper atmosphere reflected sunlight long after dusk, creating bright nights across Europe and Asia, where people could comfortably read newspapers at midnight. While the entire northern hemisphere witnessed this glowing aftermath, the physical site of the catastrophe remained locked away in the unreachable Russian taiga. Investigating the site required resources the Russian Empire could not spare. With the onset of World War I and the subsequent Russian Revolution, severe geopolitical conflict prevented any organized scientific expedition from reaching the blast zone for nearly 2 decades. In 1921, a Soviet mineralogist named Leonid Kulik finally secured state funding. His motivation was practical. He believed a massive iron meteorite had struck Siberia, and he intended to claim the valuable metal for the Soviet government. Reaching ground zero in 1927 required a grueling trek through the Siberian wilderness. Kulik's team battled extreme cold, disease, and thick swarms of mosquitoes, all while struggling to navigate with hesitant local guides. Local Evenki shamans believed the devastation was a punishment dealt by the thunder god Ogdi. They placed the forest under a strict cultural quarantine. This taboo kept people away, unintentionally preserving the site from looting or tampering for 19 years. When Kulik finally breached the epicenter, he expected to find a massive crater holding a solid iron core. Instead, the landscape presented a physical paradox that confounded the scientific consensus of the 20th century. Kulik photographed a massive field of destruction. 80 million scorched trees were pushed outward, knocked flat in a distinct 2,150 square kilometer radial pattern resembling a spread-eagled butterfly. But the map's center reveals an impossibility. At the exact epicenter, trees were stripped bare yet left perfectly upright. Furthermore, there was no crater, and not a single meteorite fragment was found, entirely contradicting the mechanics of a cosmic strike. This physical evidence split researchers into opposing camps. The asteroid theory neatly accounted for the massive ground damage and microscopic mineral traces found in the soil. Meanwhile, the comet theory, proposing an object made of ice and dust, better explained why the object completely vaporized and why water vapor clouds illuminated the skies over Europe. With no crater to measure and no surviving rock to excavate, the Tunguska mystery could not be solved by digging in the dirt. The answer required an understanding of the atmosphere itself. Decades later, scientists at institutions like Sandia National Laboratories utilized modern supercomputers to recreate the fluid dynamics of a high-speed atmospheric entry. These infographics map out the mechanics of an airburst. When an incoming rock traveling at 60,000 miles per hour hits the dense lower atmosphere, the air in front of it compresses and heats up rapidly. The extreme pressure forces the object to flatten and catastrophically detonate 5 to 10 kilometers above the surface. This mid-air detonation sends a violent jet of heated gas and a highly pressurized shockwave straight down. Trees directly underneath catch the force vertically, stripping their branches while leaving the trunk standing. Trees further out catch the wave at an angle and are knocked flat, perfectly matching Kulik's observations. We have empirical proof of this exact phenomenon. In 2013, a smaller-scale airburst over Chelyabinsk, Russia, blew out windows and injured hundreds, leaving a massive smoke trail in its wake and proving the destructive power of a mid-air detonation. The crater at Tunguska was missing because the weapon that destroyed it never reached the ground. The Earth's own atmosphere acted as a concrete wall. While we now understand the mechanics of the explosion, the lack of a confirmed physical fragment leaves room for debate, keeping fringe theories, like the proposition that nearby Lake Checo is actually a hidden impact crater, circulating among researchers today. Tunguska serves as empirical proof that catastrophic, city-killing cosmic impacts occur within modern human memory. The realization of how close the 1908 blast came to a major population center birthed modern planetary defense initiatives. This includes active space missions designed to deliberately crash a spacecraft into incoming space rocks to deflect their trajectories. Today, the physical scars at the epicenter have healed. A vibrant, regenerated forest now covers the landscape, hiding the violence of the past century. The Tunguska Event was a cosmic warning shot. Earth is continually orbiting through a planetary shooting gallery, leaving humanity with one lingering question: will we be ready the next time the sky splits open?